Now we are on to our last session. Uh, a good atmosphere, packaging, and micropollutants. Our second talk is with Artur Neves. Please turn on your video, Artur. Artur
Hello.
is, hello. Artur is a PhD candidate at the Nova School of Science and Technology. Focused on cellulose nitrate degradation mechanisms, his project aims for better preservation of cellulose nitrate heritage. This year, he received a research fellowship within the Nemocine European project to study the degradation of cellulose derivative cinematographic films. Take it away, Artur.
Thank you very much for the kind introduction. And I would also like to thank the scientific committee for the opportunity to talk about a smart future for cellulose derivative conservation, driven by the innovation of the Nemocine project. So in the digital era in which we live upon, the term smart has been widely used, for example, in smartphones, smart cars, smart homes, and the like. The title of my talk was inspired by this paper on the Journal of Innovation and Knowledge by Lee and Trimi, in which they give a broad definition on the concept of smart future, how to achieve this future, and how it will shape society. In summary, a smart future is where intelligent solutions to complex problems are achieved through collective work and through the application of the available technology and knowledge to create new value in a fundamentally different way from the past. The concept of smart is not strange to cultural heritage and its preservation. Chinese and co-workers defined the interaction between individuals, sensors, and the production, collection, and processing of information as a big smart space. The role of technology in a big smart space must be that of a mediator between people, enjoyment, and preservation. For the case of image heritage conservation, the Nemocine project will create this kind of mediating structure that will allow a smart future for cellulose derivatives conservation. The Nemocine project has the aim to improve the traditional storage solutions, such as freeze storage, by developing an innovative smart package with the main goal of energy saving and the extent of conservation time of cultural objects based on cellulose derivatives. Below, you can see the initial concept design of the smart package with a series of features from which I will talk some of them in this presentation. I am sorry if I do not go much in detail technically in some specific developments, as they are still taking place and are confidential. This project is composed by a consortium of 18 partners that range from archives, university, R&D units, plastics industry, or conservation materials manufacturers. It is important to stress out the multidisciplinarity of this working group, as the innovation pursuit is only possible through a great collaboration between partners. When I mentioned cellulose derivatives and the Nemocine project, I talk mainly about cellulose nitrate and cellulose acetate, predominant materials in the photography and cinema heritage. As had been discussed in this conference, cold and frozen storage are well accepted in the conservation community as the best storage conditions to preserve cellulose nitrate and acetate, especially in collections of image heritage. This is due to the pioneering works of the Image Permanente Institute beginning in the 1970s. Having proved that the colder the temperature, the longer the useful lifetime of the collection, they were able to build the first cellulose acetate degradation predictive models, the API wheel, or the storage guide for acetate film, that would tell us the time that it could take of a film in good condition to reach the autocatalytic point, a 1.580 strip. These tools were so successful that they created a new conservation paradigm for this heritage by helping the conservators and archivists in their decision making. Although cold storage presents its disadvantages, and already discussed here in this conference, which were already stressed out by the image permanence time out of storage table, a degradation predictive model that accounted with the days that the film could be out of storage, for example, display. The table shows that even 1 day out of storage could have a very negative effect on the material lifetime, limiting accessibility. Furthermore, questions have been raised due to price-sensitive nature of cold storage, its energy costs, physical damages if relative humidity is not controlled. And recently, a new predictive model was built that shows that the lifetime of the films in cold conditions can be lower than the proposed in the current guidelines. A second fact to bear in mind about the time estimates is that the actual behavior of the nitrate and acetate films in real life will be determined not only by temperature, relative humidity, or storage conditions, but also due to its packaging. Currently in archives, such as the Portuguese Anheim or the Italian Alinari, we can find three types of packaging: the steel and aluminum film cans, the archival cardboard, or the polypropylene cans. Steel and aluminum are unsuitable. Iron is a catalyst. Aluminum is better, but it's also with catalyst. Paper cardboard are unsuitable because they generate acids during storage. The propylene film cans, for example, the Provent and Denken solutions, are the best available options. These containers have ventilation slots that facilitate our exchange and reduce the acetic acid concentration inside the film cans. However, in the core of the film, the concentration of the acid is the same as in the non-vented can. And as we now know from the previous talk, we can have a higher loss or rate loss of the plasticizer in a vented can. Cold storage and polypropylene containers are solutions that already exist for more than 20 years. There has been innovation for film preservation, such as the pickle film and the pickle box. The pickle film have a lifespan of at least 500 years when stored under standard conditions, that the owners avoid the risk of migration and a more predictable long-term cost of the collection preservation. But as in general duplication procedures, does not account with the original's preservation. And as Jose Oraca stated, it is important to keep the originals. Original preservation is required because it is well known that data migrations, even if it's only one time to the pickle film, involve a risk of data loss or corruption. Furthermore, there are film properties that are only possible due to their cellulose derivative supports. So going back to our smart box, we can now understand better some features that we are looking for: a chemically inert and highly stable packaging solution, energy efficiency, since cold storage raised some questions. Because we know that cold storage is price sensitive, big collections may have the conditions to apply it, but small cultural associations or even individual micro collections cannot. So they may resort to duplication, and again, we have the risk of original loss. So we want to offer a low-cost option to these small collectivities or individuals. It is also very important to selectively absorb the accumulated degradation gases. Of common knowledge today, cellulose nitrate and cellulose acetate are highly unstable due to their chemical properties. Cellulose nitrate degradation leads to the loss of the nitrate groups, decrease of the degree of substitution, emission of nitrogen oxides, and formation of nitric acid. Cellulose acetate acid catalyzed hydrolysis leads to the loss of the acetate groups, decrease of the degree of substitution, and emission of acetic acid, which further catalyzes degradation. Much of this knowledge comes from, again, the pioneering work of the Image Permanence Institute that correlated the acidity level and degradation, achieving a valuable for the autocatalytic point. They developed the most important diagnostic tool, the AD strips, that correlated the concentration of the emission of acetic acid with the film's acidity level and thus degradation. And so, inspired by the AD strips and looking back to the requirements for a smart future, we will use the available technology and knowledge to create new value in a fundamentally different way from the past. And this will be the smart component of our box. We will include gas detecting sensors to monitor acetic acid and nitrogen oxides and correlate those signals with degradation predictive models for cellulose nitrate and cellulose acetate. These sensors will also alert the user or when the gas absorbers must be changed inside the box. Now, going more technically detailed, I will talk about these three features related to the smart box. The project is developing functionalized metal organic frameworks which will absorb acetic acid with high selectivity. MOFs present advantages over common absorbers as researchers can control the framework topology, porosity, and functionality. On the left, I show structures of MOF MIL 140B and IOI 66 and H2, which have been investigated for acetic acid absorption on the published work that I present to you. And how will these MOFs be used in the smart box? A good material operability will be achieved by integrating the MOFs in innovative, inert, and stable structures. Foams, fibers, and paper sheets are being investigated. Studies on antifungals with controlled release mechanisms are also being investigated and will allow an active packaging solution to minimize the growth of fungus in the films. For the measurement of the concentration of gases inside the package, Biosensor, a partner from Nemazin, developed an array which integrates sensors of NO, NO2, and acetic acid. The values obtained with the acetic acid sensor showed good correlation to the AD strips. The volatile compound sensors array main advantages over the AD strips are the time required for the measurements, it only takes 15 minutes, the reusability of the platform, and the possibility to perform remote monitoring of the conditions in the storage area. It will also give the information on when the moss adsorbers must be changed. Work on these sensors has been published. A crucial feature of the box will be the correlation of the sensor signal with the degradation of the films. This tool will allow conservators and archivists to know more about their collection condition and do better decisions regarding its conservation. This project has already developed a degradation predictive mathematical model that was submitted to the SES Omega journal. This model has been validated by the analysis of the degree of substitution of cellulose acetate references using these developed FTIR calibration curves that I show on the left. A chemometric model based on the degree of substitution analysis of historical films is now being developed for the mathematical correction factor. Also mentioned the work by Julien Kamer and Bertrand Lavetrine, which used a prototransfer reaction time-of-flight mass spectrometer to evaluate the R composition from 41 films dated from the second half of the 20th century, with different degradation levels. This work provided valuable insights on the emission of films and also proven to be a powerful tool to monitor in real time objects degradation in museum environments via the quantitative and qualitative analysis of their emissions. A prototype of the box has been designed and 3D printed. This modular package will allow the change of the sensor depending on the film stored, cellulose acetate or cellulose nitrate, or the use without the sensor array. The design of the package will allow stackability. The designed solution also considers a controllable ventilation function, which optimal ventilation in case the end user chooses not to use it. The smart package will be chemically inert and made of highly stable packaging materials, resistant and truly tested to meet the requirements of preserving this precious and fragile cultural heritage. You can look for this information in more detail in the second newsletter available in the project website. The efficiency of the designed box will be compared with other available solutions using the apparatus presented in the last slide. The Nemazin project is an effort for a smart future in cellulose derivatives conservation, as it also accounts with the preservation of three-dimensional objects and artworks. Here, I symbolically placed the Namgabu construction in space 2 cones from 1927, as we know that it severely degraded to a point that it could no longer be exhibited. Adapted Nemazin boxes promise a better future for cellulose nitrate and acetate artworks conservation. In my PhD project, I intend to develop intelligent conservation solutions based on Nemazin for packaging of three-dimensional objects, having been donated to our institution a cellulose collection of more than 300 objects as case study. It is also possible to visualize the development of smart display solutions for these objects based on the Nemazin technology. To conclude, in my opinion, in the future, smart will be a concept well established in plastics conservation, as the digital era imparts with it necessarily the use of big data, smart analytics, or networked smart sensors. Thank you for your attention.
Thank you, Artur. That was wonderful.
Thank you very much.
Our third talk is with Mary Coughlin in a recording. Mary Coughlin is an associate professor in museum studies at the George Washington University in Washington, D.C. Previously, Mary worked at the Smithsonian's National Museum of American History, where she conserved objects as diverse as FDR's leg braces and Star Wars C-3PO and R2-D2. Very sexy objects. She has an interest in the challenges of contemporary museum collections, particularly with respect to plastic. And if you were here a few days ago, you will have already seen her. Roll the tape.
Hello, thanks for joining today to hear about my exploration of repurposing ozone test strips for monitoring degrading PVC plastics in museums. In the Journal of the American Institute for Conservation's special issue on collection care, Ellen Perlstein noted that a product called ozone test strips could get a false positive in the presence of other oxidative reagents such as chlorine. Knowing that most PVC plastics contain a high level of chlorine as part of its manufacture, and that hydrogen chloride can be emitted as it degrades, got me thinking that perhaps ozone strips could be repurposed for detecting deteriorating PVC in museums. Since World War II, polyvinyl chloride, or PVC, has been one of the most commonly used thermoplastic polymers in the world. A commonly seen problem in museums with flexible PVC is that its plasticizers can leach out as it degrades, resulting in weeping and deformation. Phthalates, particularly DEHP, have been a commonly used plasticizer in PVC since the 1950s, though its use in certain products began to lessen around 2010 because of health concerns. Pictured here, you see examples of plasticized PVC that were evaluated as part of this study. They range in date from about 1985 to 2015, making it likely that several, if not most, are plasticized with DEHP. If PVC is plasticized with DEHP, those molecules can be vulnerable to oxidation and form phthalic acid, which is difficult to visually observe until an advanced stage of degradation, typically indicated by a strong odor and discoloration. Dehydrochlorination, an autocatalytic reaction in which hydrogen chloride is removed, is a primary degradation pathway for PVC. The gaseous hydrogen chloride forms hydrochloric acid with atmospheric water. Exposure to high temperatures and ultraviolet light, as well as alkene defects in the PVC chain ends, promote dehydrochlorination. Therefore, in a museum context, knowing if PVC is emitting an oxidant such as hydrogen chloride or forming an acid such as hydrochloric acid or phthalic acid could provide insight into how PVC collections are aging and influence storage and display decisions. Having an easy-to-use, inexpensive method of detection would greatly benefit the many museums who do not have access to analytical equipment for identification of plastics and degradation products. With funding from the George Washington University and the assistance of scientists from the Smithsonian's Museum Conservation Institute, myself and a graduate student spent the winter and spring of 2018 exploring the application of ozone strips for plastics monitoring. Additional testing then occurred the following year at the university. Macrinago produces commercially available ozone test strips that turn through shades of light yellowish beige to brown, depending on the concentration of oxidant present. You can see the color scale on the side of the packaging. With the darker the reaction, the higher the concentration of oxidant. According to the manufacturer, ozone test strips are made with potassium iodide starch paper, so a product marketed as potassium iodide starch paper by Macrinago was also purchased. Analyzing both strips with XRF showed some differences, and in testing with PVC samples, they did not perform similarly. This, combined with the need to wet the potassium iodide starch papers for testing, led them to only briefly being studied as part of this project. Here are the general phases of the testing that we carried out. I won't go into details of them all today, but in general terms, we first tested the strips by exposing them to hydrochloric acid. We then used a pollutant generator to evaluate the sensitivity of the strips to chlorine. Next, we evaluated the reaction of ozone strips and AD strips sealed in glass beakers with plastics identified using FTIR and XRF. Images of reacted ozone strips were taken using a USB microscope to better see reaction locations on the strips. And finally, images of the strips were then taken on a flatbed scanner and looked at with a raster graphics editor to loosely quantify the red, green, blue color changes, since the shifts to shades of yellow and brown indicate the level of oxidant present. Now for more details about the key aspects of the testing phases. When ozone strips were put vertically inside a bottle of hydrochloric acid, all of the strips changed color around the edges within 5 minutes. Over time, the color reaction occurred in the center, but remained darkest at the edges. Strips that were cut smaller had quicker, darker reactions, likely because of the increased surface area. When strips were placed on the opening of the bottle, rather than hanging down inside of it, the reaction took longer and was more subtle, confirming that the more concentrated the oxidant, the quicker and darker the reaction of the test strip. To try to determine the sensitivity of the strips, we tested with known dilutions of acid using a pollutant generator. The pollutant generator setup was first tested using acetic acid in 80 strips, since the reaction is well established. 80 strips will change from blue to shades of green to yellow in the presence of acids, with the quicker and more yellow the reaction, the more acid present. The bromocresol green dye on the strips are light sensitive, which will come into consideration later on. This testing confirmed that the test design with the pollutant generator worked. We then moved on to testing ozone strips with a hydrochloric acid permeation tube in the pollutant generator. However, we could not achieve a reaction. After speaking with a chemist from the company, it seems likely that the hydrochloric acid permeation tube analyte concentration was too low to get a reaction that was quick enough for us to observe, even after raising the temperature in an effort to drive the reaction. For me, this was a lesson learned to ask to talk to a chemist rather than the sales rep when ordering. I just didn't ask the right questions. But thankfully, the chemist guided me towards an option that did yield results. We next tested the ozone strips in the pollutant generator with a chlorine wafer. This showed that the ozone test strips are reactive to chlorine and that the higher the concentration, the faster the reaction. And the longer the testing time at a high concentration, the darker the reaction, as illustrated by the two test strips exposed at 1 liter per minute dilution rate at 4 minutes and 40 minutes, pictured here. Here is a graph showing the results from the previous chart. Again, the more concentrated the chlorine, the faster the reaction. Note that the reaction time listed for the chlorine gas may not be exactly accurate because of non-continuous visual monitoring. The reaction time value of 0.953 is pretty good for visual inspection, which for us indicated that the strips have potential in real-world monitoring. We then started 2 weeks of testing in glass beakers with 3 known samples of PVC as well as a control. Rigid and flexible PVC from the resin kit of known plastic samples that were also confirmed by FTIR, as well as green safety goggles identified with FTIR as having flexible PVC sides, were chosen for the first round of testing. All beakers were sealed with aluminum foil wrapped in parafilm around the edges. Wrapping with parafilm ensured that the plastic samples were well sealed, since the larger lab environment had enough oxidants present to achieve a dark brown reaction within just a few hours. For the control, there was no reaction for the ozone strips or AD strips. Rigid PVC from the resin kit of known plastics did not react, which is not surprising since rigid unplasticized PVC tends to be more stable than flexible PVC. Flexible plasticized PVC from the resin kit was weeping and warped, which are visual signs of deterioration. The ozone strips slightly reacted after 1 day, seen here, and the reaction increased after 4 days and 1 week. The AD strip did not react, which may indicate that acidic off-gassing is not occurring or is below the detection limit. Green safety goggles with PVC sides that were weeping and tacky were also monitored. There was a positive reaction of the ozone strip noticeable after 1 day, seen here, and a slight increase in change at day 4 and day 7. The AD strip did not change, which again may indicate that acidic off-gassing is not occurring or is below the detection limit. Since the initial tests were encouraging, we then moved on to additional testing. This yellow duck bath toy had no observable signs of deterioration. It was not weepy, tacky, or distorted, and there was no noticeable odor. It was previously identified as PVC using the Beilstein burn test for halogens, and XRF detected the presence of chlorine. FTIR confirmed the duck as PVC, likely with DHP plasticiser, and the spectrum indicated that the plasticizer seemed to be relatively intact, in a reasonable ratio, and that the PVC polymer itself did not appear to be degraded. The ozone strip reacted after 1 day, and the color change increased over the course of 2 weeks. The AD strips did not appear to change until 2 weeks, though the reaction was subtle, and this could have been caused by light exposure. Here you see images of ozone test strips exposed to the yellow duck taken with a USB microscope. It is interesting that unaided, the reaction of the strip after 1 week seemed more subtle, but when viewed with magnification, the reaction is more obvious. The reaction is darker around the edges as expected. For those keen and observant folks in the audience, you may be wondering how I took images at 1 week when I just told you I monitored the toy duck for 2 weeks. Well, rest assured, of monitoring to make sure I could be confident in the results, and the 2-week test was not compromised to get these images. We then tested another duck bath toy. XRF detected chlorine in this patriotic American white duck, and FTIR analysis identified it as plasticized PVC. However, there are some key differences from the yellow duck. FTIR indicated that a significant amount of the plasticizer is leached out, and identification of the plasticizer was not conclusive. Some peaks suggest DEHP, which would be likely since it has been the most widely used plasticizer for PVC, but there are significant differences in the aliphatic CH ranges, which could be due to side reactions or a different plasticizer. FTIR also indicated a significant degradation of the PVC polymer itself, possibly due to loss of hydrochloric acid from both chain defects and exposure to UV light and/or heat. The ozone strip reacted after the first day, with more obvious reactions after 1 week. The 80 strip reacted after 1 week, which seems to confirm the presence of an acid, such as hydrochloric acid or possibly phthalic acid from the plasticizer. This acidic reaction seems to support that the PVC is further along on its degradation pathway. Here are the FTIR spectra for the toy ducks. Since neither duck bath toy showed visible signs of deterioration, but the ozone strips reacted, the strips appear to be able to detect degradation before signs are obvious. Since 80 strips only reacted to the white duck, which through FTIR analysis was revealed to be more degraded, the ozone strips appear to be especially sensitive to PVC even at early stages of deterioration where acids are not present in levels detectable by 80 strips. Therefore, it seems that ozone test strips may have a potential to serve as an early warning monitor for PVC collections. Clear goggles with flexible weeping discolored sides were then identified as PVC with FTIR, and the presence of chlorine was detected with XRF were then monitored. The ozone strips noticeably reacted after 1 day, and the reaction progressed over the course of the week to the level you see here. The darker reaction along the edges is particularly obvious. After 7 days, the 80 strip shifted from the original dark blue to be more turquoise, indicating that acidic off-gassing is present at detectable levels. In a second phase of testing in 2019, about a year after the testing results you just saw, the reaction of the ozone strip was less obvious, and it took 3 weeks to get the same color reaction that had been previously noted after just 1 week. Why was this? It should be noted that the 80 strip mimicked the results of the previous year at the 1 week point and turned greener as testing continued over the month. In order to understand the different results of the ozone strips, I reflected on what I did with the clear goggles after the initial testing. After I packed up from testing in the Smithsonian lab, I left the goggles in the open for about 6 months before retesting in 2019. I speculate that the ventilation reduced the oxygen concentration and slowed the reaction of the ozone strip. I then wrapped the goggles in aluminum foil for 4 months and tested again. And sure enough, these results mimicked the original dark reaction observed after 7 days, and actually appeared to be a bit darker. So before monitoring, it may be advisable to wrap plastics to concentrate any oxidants that may be present to expedite testing. A cluster of grapes purchased from a craft store over 10 years ago were identified as PVC with FTIR and monitored. The grapes are still in good condition with no obvious signs of degradation. Neither the 80 strip nor the ozone strip reacted after 2 weeks of testing. To me, this indicates that ozone strips can't be used to identify PVC in general, but rather may have a role in identifying degrading PVC, which is an important distinction. In searching for other chlorinated plastics to test, a sample of polychloroprene, more commonly called neoprene, was donated from a scuba shop and monitored. Neither the 80 strip nor the ozone strip reacted. It could be that the sample is not degraded, or if deterioration had started, the ozone strip was not sensitive to it or was below the detection limit. In December 2019, when I was unpacking Christmas ornaments with my family, I smelled an acrid smell that I was pretty sure was degrading polyurethane. I then found the culprit, a piece of red foam that was part of a packing from an ornament dated as 2001. It was not surprising that a piece of 20-year-old foam would be having issues. The foam was confirmed as polyurethane with FTIR and monitored in a glass beaker with an 80 strip and an ozone strip. The 80 strip turned turquoise after 2 days, and after 1 week, the ozone strip still did not react. To me, this was exciting because it meant that the ozone strip seems to be sensitive to degrading PVC, rather than sensitive to a range of deteriorating plastics. So I thought, hooray, it's working. Or is it? I tested a butter dish with FTIR as polymethyl methacrylate, more commonly referred to as acrylic. It made its way into my plastic study collection because my husband put it in the dishwasher years before an impressive network of cracks formed in it. During testing, the 80 strip never reacted, which is encouraging because we consider acrylic to be stable. However, after 1 week, there seemed to be a very slight reaction to the ozone strip. Could it be that it absorbed oxidants from storage over the course of a decade in a single box with mixed plastics that included degrading PVC? Could it have absorbed oxidants from the dishwashing detergent it was exposed to when the cracks formed? At that point, we pulled it from the testing and analyzed it with XRF, but no chlorine was detected, nor was anything unexpected present. In the original 2018 test, the acrylic butter dish went from being stored with a mixture of plastics that included degrading PVC to directly being sealed in the beaker for testing. In 2019, the butter dish was left in the open for 1 week before retesting. Retesting did not have noticeable results in the ozone strip or AD strips until 5 weeks, and even then I was questioning if there was a color change in the ozone strip. It is assumed that over the 5 weeks, the 80 strip reaction would have more to do with light fading than an actual positive reaction for acidic off-gassing. Here's the magnified ozone strip exposed to the acrylic butter dish for 5 weeks compared to a control. You can see that even at the more reactive edges, there does not seem to be a positive reaction. Does the testing with a butter dish show the impact ventilation can have in preventing the buildup of plastic degradation products that can then be absorbed by other materials in the vicinity? But before we vent all our PVC, we must consider that studies have shown that storing plasticized PVC in non-absorbent containers slows plasticizer loss by maintaining the equilibrium with the surrounding environment. I thought it would be helpful at this point to see the results in one place of the various plastic samples utilized in the study, even though I didn't cover them all today. The different reactions of the AD strip seem to indicate that acid was not always present at a detectable level, but that monitoring with both strips has its benefit. For example, the white duck appeared to be in good condition, but both the ozone strip and AD strips reacted, and based on FTIR analysis, this PVC object is severely degraded. So it seems that ozone strips react to oxidizers, and the AD strip reacted to acids that were released as part of its deterioration, thereby giving a fuller picture of its condition that was otherwise not evident. To conclude, here are some key takeaways and recommended protocols. Ozone strips seem promising as a low-tech, accessible monitor for identifying PVC that is emitting an oxidant, but unless PVC degradation is underway, a reaction will not occur. But that does not mean that those are stable plastics you don't have to worry about. It just means you should periodically check on them and monitor over time. I want to again acknowledge the help of kind and brilliant people at the Smithsonian and the George Washington University, and thank my kids who unknowingly donated some of their plastic toys to this project. Thank you for your attention, and I welcome your comments, thoughts, and questions in the breakout room after this session.
Thank you, and I hope you'll also be willing to talk to us now.
Yes, definitely.
That was more of a rhetorical question, of course. I'm glad we get to see you again, Mary. Hello, everyone. Argyro, you have question number 1, and that is how and why did you decide on the parameters you used for the aging process in the climate cabinet? And according to that, what about natural aging?
Okay, yes. So the parameters that we used were taken from literature from other fields, such as like food like literature, where migration of plasticizer from plastic package is happening into food. And so we had to take the parameters, the values of our parameters from other like fields, because it was very hard to find the parameters from the specific plastics and plasticizer within the heritage context. We also use some literature of plasticizers and plastic and plasticizers degrading inside the climate chambers from fields that investigate compounds in the atmosphere and the effect of the plasticizers that have in the health of people. And so these are other fields that we have to investigate to take the parameters from. And the second part of the question was, sorry?
What about natural aging?
Yes, for that reason, we have set up an experiment at Tate and Museum of London, where we have prepared samples in our lab and also have some real objects, some combs donated from a collector. And we have placed them in like open and closed, in open areas at the two museums and inside the closed boxes as well. And we want to investigate that so as to be able to compare the degradation in natural conditions and in an accelerating aging experiment.
Thank you. All right, a two-part question for you, Artur. What is the final goal of the Nemocina project? To provide a new storage box and also new storage guidelines? And will you also include the monitoring of 3D objects in the Nemocina project?
Okay, so the objective is to provide a box with those features to the archives, to the small collectivities, and to individual persons that want to better preserve objects or films that they have in their houses. We will develop these sensors. That's the acetic acid has already some published work that will be correlated with the degradation models. And then we will have an interface that the user can use that will give the indication of the film condition during time. So that's really our objective, is to have a smart box that is continuously giving information to the user on the condition of the object placed inside the box. And this can be a very impactful tool, since you can do, for example, in big archives for photography and cinema that are the main focus of the project, to do this monitoring in a remote way without using the aidship and having to do that visual monitorization.
I guess for me, the big question is, you're working with film, and in contradistinction to many other areas, the film industry has a lot of money and they're very narcissistic. So are you going to get money from the film industry to develop your project? Or are you looking at that, or have you explored that?
With the film's investigation, we are already doing it. It's the main focus of the Nemocina project, the European project. We have the European funding, and we will have in the end this box to offer to the community and to the film industry if they want to use it. And they will probably be the ones that will acquire the full set of the box with the sensor, with the model, with the absorbers, because we know that a box with the sensors and the absorbers will be more expensive. So there will be archives that probably can only afford the box and the absorbers without the sensor functionality, but institutions with more money can then afford all the functionalities.
But they're not angel investors in your Nemocina project,
No.
just pumping the billions to you to do it.
No. For my PhD investigations, it would be good to have that sort of funding, yes.
Great. Okay, Mary, does a color scale exist for the color changing of ozone strips from dark blue? What color could they reach? And you mentioned a certain light reaction. Could that be a disturbing and limiting factor?
So just to clarify, this is a question about the AD strips, Katja?
This is not known to me. I am reading from Slido. It's kind of three parts. So let's start at the first part. Does a color scale exist for the color changing of ozone strips?
Yes, on the package itself, there is a scale, and there's different directions that come with it because it's meant to test for ozone typically outside. So they say you could get a reaction in 10 minutes in the outside environment, but we just repurposed for inside, assuming that the scale, and it did seem to sort of still hold. So there is a color scale on the ozone strips themselves.
And so what is the color scale from the dark blue? So maybe take us through the steps.
Okay. So for the ozone strip, the scale is sort of a beige, yellowish brown scale. So it's going to go from white to beige to maybe like a tan to more of a brown. And then the blue scale is those 80 strips that were mentioned in Artur's talk too from the Image Permanence Institute. And those start from a very dark blue and then can sort of shift to turquoise, to green, to yellow. And the more yellow they get, the more acid is present. So it's 2 strips.
This is very helpful. Okay, so now you mentioned a certain light reaction. Could that be a disturbing or limiting factor? That's the last part of this complex question.
Sure. So there isn't the dye on the 80 strips is bromocresol dye, and that does have a bit of light sensitivity to it. And I reached out to IPI to sort of gauge, if you're testing in an environment that has artificial light and some natural light, what is the duration you could test for and be confident in? And it was about 2 weeks. So that's why I stated that.
Great. Argyro, question number 2. Bulk loss of plasticizer measured with NMR was measured at the surface or in depth of the samples?
So actually, a piece of, I think it's 30 milligrams representing the whole sample was taken, and the analysis was based on this. So actually it is a slice from our sample, which is represents the whole sample, but we call it bulk because it is mainly bulk. So it's not a cut from the surface. I don't know if that makes sense.
Yeah, thank you. Artur, which temperatures did you determine for cool, cold, and frozen? If you could share that.
Well, I didn't determine any. So what I used in the presentation was cold storage below 5 degrees, and then the freezing temperatures can go to the -20. I know that, but I'm not. So what we know is that the guidelines propose cold storage and freezing using these kind of temperatures. And what we want with the Amazon project is offer a solution where collectivities that cannot apply cold storage can use. And even if an archive or an institution wants to use this cold storage in their conservation as a conservation method already, they can use the box as an initial phase where they will put the films that are still in good condition, and then the box will alert when to transfer for the cold storage, because the cold storage benefits are undeniable. The box will will extend the conservation, the lifespan of the objects, but at time probably the.
We can't hear you so well. Say it again. At the
now
time.
You hear me?
Yes.
So the box will extend the lifetime of the lifespan of the objects, but at the end the objects will probably have to go to cold storage.
So it's kind of a gateway into buying time for the objects and for the institutions.
Yeah.
This is a great solution also for institutions that don't have the capacities, as we've been seeing throughout the conference, that there are different financial resources at play, especially outside of the Northern Hemisphere. All right, Mary, during the test in the sealed glass beakers, did you also take into consideration preventing direct contact between the objects and the strips?
We tried to avoid it, and there was never contact with the ozone strip itself, but sometimes there could have been some contact with the AD strip.
Argyro, which model are you using?
Which? So our
This seems like a very open question to me. Maybe you use different models and can talk about the different models that you've been using for which things.
So this is a model based on the mechanisms that I mentioned in the presentation. So it is a model which describes the diffusion, then the mass transfer, and then either the accumulation in the chamber for closed sample or the mass transfer further. So it is a model based on these mechanisms and based on the equations that describe these mechanisms.
Thanks. Artur, did you do any kind of survey to capture the needs that colleagues would formulate for film storage, or is this derived from a common standard?
The project did a survey in the beginning to assess those needs and the specifications that some archives wanted. In this box, I can tell that we have 4 partners, 4 archives in our working group in the project. There is the Alinari from Italy, the Deutsches Film Institute, the Austrian Science Academy, and the Institut Valencià de Cultura in Spain. So, for example, those 4 archives are working directly with us and are giving their opinion and expertise on the conservation of the films and photography also.
And are any of those survey results published anywhere so that people would know what the questions were or what the input was?
No, and I don't know if they will be. And they are confidential within the project still. So it's the only the only answer I can give right now.
Thank you. Mary, how would you recommend using ozone strips in a real storage situation? Would you need to keep air volume around PVC objects low to ensure a concentration of CI?
You would, because otherwise you're just testing the whole environment. And you're definitely going to get oxidants in a lot of cases. So there is limitations perhaps in size and then how you could seal that up. I mean, everything I chose could fit into the standard beakers we had in the lab. So if you were testing something large, yeah, you'd probably have to figure that out. The other thing that I wanted to explore further and didn't get to yet is the volume of the beaker itself. Like, should there be some sort of proportion to the size of your object within the container? And how does that volume of air affect results? So my hope is that this will seed other people to explore and share.
Great. Let me just pause at this point. Do you have any questions for one another? No. Okay. So then we'll continue with Argyro. Does the smaller loss of plasticiser in a closed environment depend on the equilibrium and concentration in the atmosphere surrounding?
Well, yes, in terms of the volume inside the closed storage is smaller compared to an open area. So the equilibrium concentration will be larger, so the loss would be smaller.
Artur, what type of smart analytics would you use? Could people adapt or build their own algorithms for their specific needs?
In the end, I believe we can do that, applying what we are doing in Amazon. In the end, I believe that will be a future for conservation. Then customizing our needs for our specific objects, but using this technology of sensors, of predictive modeling, of the analysis of large data that these sensors, for example, can provide us. So I think that will be the future. So Amazon, it's a pioneering work, I think, in that sense. But going forward, I think people should start doing more of this kind of investigation using this technology.
And do people have to get new skills to be able to be smart in a different way?
I think, as Tia emphasized, I think we need to have collaborations mainly. The project, we can only achieve this result with those 18 partners. So we have to look for collaborations.
Thanks. Mary, do you think it's worthwhile to verify the materials and oxidation via Odile test, maybe to include metal coupons in correlation as another cheap way to monitor?
Could be, especially for if you wanted to do a long-term monitoring. So sort of doing a variant of the Odile test, right? Like just leaving the coupons in the storage container or the cabinet could be interesting, and maybe an interesting addition to the test.
Argyro, you had a look at plasticizers. What's the influence of the acetic acid?
So this model doesn't take into account that mechanisms as well, but we are working on incorporating this mechanism into the model so as to be able to actually make a prediction on degradation caused by more than one mechanism. So because these, like the acetic acid and plasticizer laws need different like storage. So we want an open storage to actually yeah, we need the open storage for releasing the acetic acid, and we want the closed storage to inhibit plasticizer loss. So these two mechanisms are like competing, and that's why in order to be able to predict degradation in a more like complete manner, you need to incorporate both mechanisms, and we are now working on that. So I guess that would be very interesting to have these results in the future and discuss upon this because of the competency of these two mechanisms.
At Plastics in Peril 2021.
Hopefully.
All right. Artur, which absorbers do you intend to use for CN in the packaging?
I'm already unmuted. So for CN, we are not developing any kind of absorbers. So we could use inside the box what we usually use, for example, activated charcoal. We know that it might have problems. It might absorb also the plasticizer camphor, but at this moment, we are not developing absorbers for cellulose nitrate, only for cellulose acetate, for exactly cellulose acetate.
So you also have an acetic acid question. This is the acetic acid question round. Can you say a bit more about the sensors for acetic acid and NO2? What are their dimensions and how do they function?
So about the sensors, there is work published for the acetic acid sensor that I can then share. The sensors are being developed by Biosensor. It's an Italian company specialized in this kind of applications. And for the NO and NO2, it's electrochemical, and it's really specific for this, and it's specific for these two gases. The acetic acid is oxide, zinc oxide, polyaniline photoluminescence sensor. And you can look, I'm not an expert, so you can then go to the published work and go more in detail in the specifications. In terms of dimensions, it will have, I believe, 15 millimeters by 35 millimeters, something like that. And that's what I can tell you. You can also go to the newsletter of Nemozin. There's also information about the sensors there.
Thanks. Mary, you don't have an acetic acid question in this round, I'm sorry. Do you feel left out? Do you want to talk about acetic? To test these strips, why did you not consider replicas for stronger results?
That's interesting. I wonder what they mean by why would replicas yield a stronger result? So, I mean, these things were things that I had in my plastics collection. Some of them were just so clearly already degrading that I thought of them as good candidates to see sort of what they'll do. And then the ones that looked fine also I wanted to test. So this was, again, a small snapshot, but in this case, I didn't see a use for replicas.
Okay, we are coming to the last round. So for you, Argyro, the simulation is done considering artificial aging results. So what about natural aged cellulose acetate?
Okay, so yeah, as I said before, we have set up these experiments at the museums, and we would like to compare our results. And of course, this model has been used at these conditions to be validated with this experimental data, but can also be used for parameters at another temperatures and make some predictions at mild temperatures as well. So these simulations with the parameters at mild conditions, we would like to compare with experimental data from the museums, and so as to have like predictions at real conditions for museums.
Thank you. Mary, did you weigh the samples before and after the experiments?
No, but again, that is something we probably should have done and could do in the future. So great idea.
All right. Artur, can you foresee when the box will be available on the market and how much it would cost? And did you account the maintenance that's required and the large scale of boxes needed?
So the project ends in 2022. So by then we have to have a box. So after 2022, there will be an available commercial option. About the costs, I cannot tell you values. What I can tell you is that we will have different options depending on your needs or on your economical capacity. So if you don't have money, you can try only to buy. You can only buy the box, or you can only buy the box and the absorbers. That would be basically the most cheap materials of the set. And if you have the capacity to buy the sensors and the modeling and the interface, you can do that. Of course, if you have a large system full of sensors in your collection or archive, you will have an energy consumption, considerable consumption. You have to do those studies to understand what will be the energy costs of having a lot of boxes and a lot of sensors, but that's what I can tell now.
Great. This was a fantastic last session. I think we should give you all a round of applause. Thank you all.